Hello, everyone. Welcome back to the final subconference of the second Young Academy of Sciences Summit. In this section, we will discuss technology and material evolution for energy storage. We kindly ask that you refrain from taking photos and recordings in order to respect and protect the copyrighted content of our speakers. Now, I would like to introduce a moderator of this section. Professor Zhi Chunyi is a member of the Hong Kong Young Academy of Sciences, chair professor at the Department of Mechanical Engineering of the University of Hong Kong. Let's give a warm welcome to Professor Zhi.
Thanks for introduction. So this afternoon session we have, in fact, we have two sessions. Session 2 will be in charge, will be hosted by me. So this session is about, technology and materials evolution for energy storage. We have three speakers. Professor Liu Qi from Department of Physics and City University of Hong Kong, and Jin Jin is from the Gaussian company as Vice General Manager in Hong Kong Institute, and Ming Li from Department of Chemistry, University of Hong Kong. So first, let's invite Professor Liu for his new cathode materials for lithium-ion batteries, please.
Hello. Okay, so good afternoon, everyone. And first, I would like to thank Professor Zhi Chunyi's invitation and give me this an opportunity to report our recent works. And the topic of my presentation today is about studies of phase transition behavior materials with advanced synchrotron techniques. Just as currently I'm a associate. What's wrong? What's my? Oh, okay. So I'm an associate professor in Department of Physics in the City University of Hong Kong. So first, I think everybody here should be very familiar about the lithium-ion batteries, because everyone has lithium-ion batteries with you. So in the 2010, you will find in the 2000 you will find at that time the lithium-ion batteries be mainly used in portable electronics, for example, like mobile phones, and laptop, and a digital camera. And in the 2010, this is a very important year for lithium-ion batteries, because at that year, and lithium-ion battery has started to be used in the electrical vehicles. Okay, and in the future, I don't believe that there will be some novel applications for lithium-ion batteries, like aerospace, military, and a smart grid. But for any time, we just want our batteries has a higher energy density, a higher power, and longer cycle life, right? Okay, so the working principle of lithium batteries is pretty easy. Here, let's talk about the lithium iron phosphate batteries, for examples. So if you go to mainland China or go to Shenzhen, you will find like a BYD electrical vehicles normally use a lithium iron phosphate cathode. So typically, for lithium iron batteries is composed of 4 different parts: cathode, anode, electrolyte, and separator. So though every individual part is important, but it's a cathode materials that determined the battery performance, especially the energy density and the cost, because cathode materials contribute about 30% of the cost of a lithium battery. Okay, so lithium batteries, you find the working principle during the charge, the lithium ions will be inserted into graphite layers. And during discharge, the lithium ion will be get out from the graphite layers and insert back to the cathode side. Okay, so this is how it's working. And for lithium batteries, you'll find water materials issues in a solid electrode. So water material issues. So there are four, right? So solid electrode. The first one should be electron transport, right? In the electron transport. The second one should be ion diffuse. And the three should be SEI, right? Solid electrolyte interface. And the number four is a phase transition behavior. So and the phase transition behavior is what I'm studying now. So why we need to investigate for structure changes, which I try to manipulate the phase transition and to fast lithium ion and the electron diffuse. So here are examples also for lithium ion batteries. So lithium ion batteries currently dominate the cathode technology for electrical vehicles in mainland China. That means 30% of electrical vehicles use lithium iron phosphate. So for this kind of materials, it has a typical Oliver structure. So that means it's not a very good electronically conductor. And especially for phase transition behavior for these materials, is quite different with a traditional layered oxide. So for example, during the charge, you'll find the content of a lithium iron phosphate continue to decrease, whereas the amount of iron phosphate continue to increase. And the peak won't shift. So that means it's a typical two-phase transition. Two-phase transition is much, much slower than the traditional solid solution transition behavior. So that's why when this materials was first discovered by the Goodyear in 1997, it's supposed this material cannot be used for a high-rate performance cathode. However, nobody knows now it's dominated the cathode technology of electrical vehicles today. Why? That's because for these materials, if you make it into very small particles, it will be a very typical solid solution behavior right here. So that means, yeah, for micro-sized lithium iron phosphate, it will be a typical two-phase transition behavior. But for small particles, nano-sized lithium iron phosphate, it will be a typical solid solution behavior as the lithium cobalt oxide. So that's why industry, normally the particle size of lithium iron phosphate should be very, very small. Okay, this is quite different as a traditional layered oxide. Okay, so in my group, we mainly focus on the in situ technicals studies. For example, like in situ ZINs, in situ X-ray diffraction, in situ PDF, and in situ TM. So, and we did a lot of in situ study. And if you want, this powerful technique could be used to study what kind of materials. For example, like coin cells, pouch cells, even the cylinder 1865 cylinder cells. Say, this is the first cylinder cells work in the world. Okay, so this is I'm done like 12 years before, 15 years before maybe. So in the argon, so you'll find that this is a cylinder 1865 cells, and even for flow batteries. So, and synchrone-based X-ray diffraction or XRs or image can be effective to study the phase transition behavior of various cathode or anode materials for advanced batteries. So in my research group, and we mainly focus on the very typical or traditional cathode materials like lithium cobalt oxide or ternary cathode materials or lithium iron phosphate, do some fundamental research and like X-ray diffraction and for long-range water structure or PDR for local structural study or exams for valence change study. And then we do some regulations, and eventually we just try to improve the energy density or power or stackability of the cathode materials as expected. And here I would like to give you guys two examples for my study. The first one, the lithium cobalt oxide. Okay, so everybody here should be has a lithium cobalt oxide batteries because everybody has a cell phone with you. Okay, the cell phone just using the lithium cobalt oxide. Okay, so you'll find, okay, why lithium cobalt oxide? So starting from market, okay, so you'll find every year thousands of publications about cathode and anode has been published. However, I have to say, and also Professor Chen should be know about that, rare improvement on the exploration of the cathode materials has been developed. Okay, so and lithium iron phosphate and NCA and NCM dominate the cathode technology for electrical vehicle applications, but for a smartphone, the lithium cobalt oxide dominate. That means 90% of smartphones using the lithium cobalt oxide as a cathode materials. Okay. So what's lithium cobalt oxide? So what kind of a phase transition behavior inside? So it has a layer structure, right? Layer structure should has a easier phase transition behavior, but actually it's not. It's very, very complicated phase transition behavior for these materials. So this is a typical in situ study for the pristine cathode and lithium cobalt oxide cathode. This is charge and this is discharge. So you'll find the phase transition behavior is quite complicated. So how complicated? Okay, so now you'll find, okay, so initially you'll find the lithium cobalt oxide has a hexagonal structure, right? Hexagonal structure also is layered structure. You'll find this is a transition metal layers, and this is a lithium ions, transition metal layers, and the lithium layers. Okay, so during the charge, the lithium layer, the lithium ions will be get out of the structure, right? So how the lithium ions is get out of structure? So if we neighbored the lithium ions, like 1, 2, 3, 4, 5, 6, 10, if we label lithium ions, so during the charge, what will happen? Initially, you'll find the lithium ions will be orderly get out of structure. So that means that 1, 3, 5, 7, 9. Okay, the lithium ion will be orderly get out of structure. Okay, so if you further charge these materials, that means if you try to get more lithium ions from these materials, what will happen? You'll find that then the lithium ions will be disorderly get out of structure. That means the lithium ions not be get out of the crystal structure in disorder. So what will happen? Then it will be trigger the phase transition. So you will find the phase transition behavior will be transferred from the hexagonal structure to the monoclinic structure. Okay, then when it transferred to monoclinic structure, when more lithium ions get out of the structure, what will happen? It will be transferred back again to its original hexagonal structure. So you'll find during charge, initially hexagonal structure, then monoclinic structure, then hexagonal structure. And further get the lithium ion materials again, you'll find is transferred to O1 structure. That means there'll be only one. There will be cause a huge lattice contraction like this, huge lattice contraction. So for lithium cobalt oxide, the higher voltage, you can get more capacity from these materials, but it will suffer either the water-disorder transition or O1 to O3 phase transition. The two phase transition will be substantially lower than lithium ion diffusion or cause a capacity decay. So what that means, okay, for your cell phone, right? Suppose it only can charge to 4.3 volt. If you charge to 4.5 volt, yes, for sure, you will get more capacity, but your battery will be, the capacity decay will be get faded very, very quickly. Okay, so this is the problems about these materials. So our strategy, and this is a very old work, and at that time I working at the Argonne Nation Lab, and at that time, okay, so the relationship between U.S. and mainland China is still very good. So at that time, we still get a fund from a Huawei company. So at that time, and collaborate with Huawei, we have carefully choose two elements. One is alumina, and one is lanthanum. So for this, the alumina normally used to suppress the water-disorder transition, and the lanthanum just try to increase the lithium ion diffuse. And at that time, for first time, we have successfully pushed this lithium cobalt oxide to 4.5 volt, and can get a capacity around 190 milliampere per gram. Okay, maybe many audience maybe don't understand what this means. Okay, here I can briefly introduce the history of a lithium cobalt oxide right here. Okay, lithium cobalt oxide was first discovered by Goodenough in 1981, and it can be commercialized in 1991. And Apple for the first time to using the lithium cobalt oxide as a cathode materials in 2007. And then at that time, you'll find it can only charge to 4.1 volt and get around 140 milliampere per gram capacity. Then 4.2, iPhone 3GS, iPhone 5, 3.3, 160, iPhone 6, 165, 4.35 volt. Okay, so what's the generation of iPhone now? iPhone 16, right? So you will find actually there will be no significant difference in the batteries between the iPhone 6 and iPhone 16. Why? Because industry, even today, the 4.35 volt lithium cobalt oxide still dominate the custom technology for the portable electronics. So if you want to, now in 2018, we have successfully charged to 4.5 volt and get a capacity around 190. Yes, we could do that, right? But there's still a lot of issues have to be resolved before eventually be used by Apple. Okay, for example, like an electrolyte side, right? So anyway, so how about in the future? I think for these materials, the theoretical capacity of lithium cobalt oxide could be reached to 274. But for me, I think the practical capacity can be reached to 220. So this is the maximum. Okay. So, and recently, Professor Zichun Yi has just published a paper in a Science Advance, and he has successfully to push the charge voltage of a lithium cobalt oxide to 4.8 volt. Okay, so I think, yeah, at that voltage, maybe the capacity is around 230 or something. But yeah, if you're interested, you can go ahead to take a look. But there's truths you have to know. Considering the lithium cobalt oxide, this is still most widely used cathode in today's portable electronics. Even a little bit like a 5 milliampere hour per gram capacity improvement of these materials have a huge impact just simply due to the scale of these materials. Okay. Okay, so this is about the lithium cobalt oxide. Now I would like to talk something about our recent work about lithium-rich cathode materials, that's cobalt-free lithium-rich cathode. There is truth, the best combination of many energy storage needs involve the cathode structure that is naturally composed of cobalt. For example, lithium cobalt oxide. Also like NCA materials or NCM materials that are widely used in the electrical vehicles. For example, like Xiaomi or Leo, just using the NCA and NCM materials. Okay, so, but cobalt is rare and expensive, right? So, why lithium-rich cathode materials? Okay, there's some type right here. Okay, now when you go to Shenzhen, okay, you will find the BYD cars for the combination of lithium iron phosphate and graphite. The battery can be reached around 180 But for NCM 523 can reach around 200, 220. But for NCM 811, so this is a typer, this should be 260. Okay, but if you want to go higher, for example, like 300 or 350, you have to need the cathode materials at least reach to a capacity about 250. So that's why we have to study lithium-rich cathode materials. Lithium-rich cathode materials is a composition of layered cathode hexagonal structure and also the monoclinic structure. So this is a lithium manganese oxide and this is a layer structure. Okay, these materials, okay, the theoretical capacity could be as high as 380. But this materials has a huge problems. Why? That's because in the monoclinic structure, you'll find some lithium ions has been inserted into the transition mantle. Okay, into a transition mantle. So during the charge, the lithium ion will first get out from the hexagonal structure, right? And if you try to get more lithium ions from these materials, it'll be start to get out from monoclinic structure, then from the superlattice right here. Okay, when the lithium ions get out of this superlattice, it won't be able to get back again. So it will be need to the local structure collapse. So this is will be needed to a huge voltage decay about these materials. So every material has a capacity decay. For example, for your cell phone, you charge for 1 day, it can be used for 12 hours. But 3 years later, if you charge 1 day, it can be only used for 8 hours. That's a capacity decay. Capacity decay won't affect the use of your cell phone, but voltage decay will. Okay, so the voltage decay, that means the voltage platinum will be continuous decrease due to the unstable honeycomb structure. Many from here, this is a superlattice right here, honeycomb structure superlattice. So when the lithium ion get out from the right here, so this local structure will be collapsed. Okay, so if you want to commercialize the lithium-rich cathode materials, you have to address the voltage decay. So in the other, so that means you have to address stabilize the honeycomb structure. Okay, so and just in the 2023, we have for the first time report lithium-rich cathode materials without voltage decay, and all these materials has been evaluated at the Argonne National Labs benchmarking facility. That's CAMP. For our materials, you will find that it can deliver the capacity around 250. And importantly, there'll be no voltage decay at all. Okay, so this is the first time that we can address the voltage decay for these materials. Before we have got a very good result, which I try to find the behind mechanisms. Okay, once again, as we have mentioned in the previous slides, for the lithium-rich materials, it has two structure. The layer structure is very stable. Lithium cobalt oxide is stable, NCM is stable, right? But for monoclinic structure, is not. Okay, you'll find the superlattice right here. Superlattice that will be form a honeycomb structure. That means when this lithium ion get up structure, and it won't get back to its original crystal structure. So, and our strategy just try to kept the honeycomb structure during synthesis. And you will find maybe we can use the synchrotron X-ray diffraction to find the effectiveness of our strategy. Okay, so this is a charge, discharge, and a charge for materials. And this is a Fox beam line. Okay, this Fox beam line is a very cutting-edge technology in the Argonne National Lab. So for this technology, for batteries, it can only be only the cathode material will be detected. So other information like anode and separator or electrolyte can be screened. So For help of this advanced technique, we could be used to find the structural evolution of a superlattice. For example, 0, 2, 0, this is a superlattice. Okay, you'll find the superlattice during the charge and discharge is quite stable and won't change, or the peak strength won't change, okay? So this is our strategy. And once a honeycomb structure has been stabilized, then the water decay will be addressed. Then we can obtain the lithium-rich cancer materials without water decay. So what will be next step? So for the next step, we just try to get some like a surface interface engineering, try to optimize these materials. Also like a morphology size, orientation particle size, electrical thickness composition change. So for the eventually, I think in the current the lithium-ion battery system, we can obtain a pulse cell. This is not a solid-state batteries or quasi-solid-state batteries. This is just in the traditional lithium-ion battery composition. We do believe we can obtain pulse cell has a 350 watt-hour per kilogram. Okay, so this is the conclusion of my presentation today. And for lithium-ion batteries, it's a cancel that determines the energy density. Okay, most of lithium-ion battery involve the cancel structure that is largely composed of cobalt. Lithium cobalt side dominate the cancel technology, portable electronics. And with a higher capacity at the low cost, cobalt-free, lithium-rich oxide are promising class cancel material for next generation lithium batteries. However, it suffered water decay issue. And now my research group can be designed and demonstrate novel cobalt-free lithium-rich cancel materials without water decay. Okay, thank you. Thanks.
We will have Q&A during panel discussion session. Yeah. Okay, our next speaker is Jingjing Liu Jingjing. He's Vice General Manager, Deputy Director of Goshen Hong Kong Institute. She's going to talk about, would you come over? She's going to talk about the systems for urban energy grids. Yeah, thank you.
On stage, we will have a panel discussion. May I invite the speakers and the moderator of this section to the stage, please? Professor Zhi Chunyi, Professor Liu Qi, Dr. Liu Jingjing, and Professor Li Aiming, please. Just now, they have discussed on the topic technology and material evolution for energy storage, and there will be a Q&A discussion towards the end of this panel discussion. Our audience, you're welcome to raise the questions to the speakers. And for now, I hand the floor back to Professor Zhi Chunyi. Professor Zhi, please.
Okay, I should get started, right? Okay, before I initiate our discussion, any questions for the past three seminars, talks? Do you have any questions? If you have a question, you can ask now.
Probably my slides has a lot of scientific data. If you want to ask and discuss anything, yeah. Now is the time. Or you can send my email. It's fine. Yeah.
Okay. Let me start with a few questions. In fact, I don't know what do you want to know, but I personally feel, energy storage is quite dynamic field with a lot of systems. Not only is lithium batteries, although it's most popular system. Then it has an evolution since the first commercialized battery by Sony in 1991, right? Around 1991. Right. So it's been evolved from, if you look into this application scenarios, from 3C products to EVs, now to energy storage, for example. It's kind of corresponding to different lithium battery systems. In fact, in terms of material systems, they're in fact different. So let me start from, as mentioned by Professor Liu, in fact, in terms of energy density, the cathode materials, I think it's very limited progress on the anode materials, always graphite, right? People starting work on lithium metals been many years. In fact, it's still quite challenging. So on the cathode materials, we achieved many important progresses. So my first question to Professor Liu is the evolution of cathode materials. Yeah.
Okay. Thanks, Professor Zhi. So actually, this is a very challenging question. Yeah. The evolution of cathode materials. Yes, because since I've been working on this field for more than 15 years, I can say some words about the evolution of cathode materials. Just as I mentioned in my slides, a typical lithium battery is composed of 4 different parts: cathode, anode, electron, and separator. Though every individual part is important, so like electrolyte. But actually, the cathode materials, just as Professor mentioned, dominate the energy density of the whole battery. So because the capacity of lithium cathode material is much lower than the anode materials, especially for the development of silicon anode materials. Okay, let's go back to the early age of discovery of lithium batteries. I think everybody here should know about the Nobel Prize 2019 has been awarded to 3 scientists for the discovery of a lithium battery, right? So Professor Winnie Ham, Professor Goodlove, and Professor Akio Yoshino. So Professor Winnie Ham in the 1970s just provide the concept of lithium-ion batteries. But at that time, he go to a wrong direction. He tried to use the sulfide oxide as a cathode materials. Okay, so 10 years later, Professor Goodlove has found the right cathode materials, just a lithium carboxide. So that's why he has been awarded the Nobel Prize. Okay, so 4 years later, and Professor Akio Yoshino fabricated the first lithium batteries based on lithium carboxide. Okay, so you will find, just as the professor mentioned, in 1991, Solid released the first lithium batteries. So you will find how important of lithium carboxide. So here, I just want to mention lithium carboxide can be viewed as a first generation of a cathode materials. For this materials, it has a layered structure, so it's very simple. Simply push this material to a high voltage, and you can get more capacity. So the higher charging voltage, the more capacity. So you maybe don't know that actually Apple company play a very important role in the discovery and the development of cathode materials. Because it just try to push the lithium carboxide to even higher voltage. Okay, so the first generation of iPhone can only use the 4.1 volt lithium carboxide with a capacity of about 140, but now it can be charged to 4.35, get a capacity around 435. But what's a theoretical limit? What's a practical limit? Not a theoretical. Practical limit about this important cathode materials, I think is around 220 or 230 milliampere per gram. So that means around 75 or 80% of lithium ions can be get out of this structure. Okay, this is the limit of these materials. Okay, so the future research direction from both academia and industry just try to put more lithium ions from these important cathode materials. That's because even today, these materials still dominate the cathode technology of smartphones, so cannot be occupied at all. Okay, so this is about lithium carboxide. So then let's move to the second one. Lithium carboxide is very expensive. It's okay for us to use in the portable electronics, right? But it's unacceptable to use in the electrical vehicles. So that's very, very expensive. So that's why they just try to occupy the cobalt with other elements such as nickel and manganese. So this comes to a second generation of cathode materials. That's NCM, ternary cathode materials. So NCM or NMC materials, that's a nickel, manganese, cobalt. Okay, these three elements. These three elements play different role in this layered oxide systems. Nickel mainly contribute to capacity, manganese contribute to stability, and cobalt mainly contribute to the charge capability. So it also experienced several generations from initially NCM 101 to NCM 523 and NCM 622 and until now NCM 811. But even today, NCM 523 and NCM 622, that means 60% of nickel, 20% of cobalt, and 20% of manganese. For these two kinds of ternary cathode materials dominate the cathode technology of high-brand electrical vehicles. For example, Xiaomi and also NIO, these electrical vehicles using these two kinds of cathode materials. So the higher amount of nickel, the higher capacity, but the also lead to some safety issues. So that means, for my opinions, so what a future research direction for ternary NCM materials, just focus on the NCM 523 or NCM 622. Try to push it to even higher voltage, like a lithium carboxide, and get more capacity from these materials. This is one direction for NCM materials. Or another direction, just try to put the amount of nickel to even higher, to 90%, or even 94, 95, right? But this kind of a cathode material cannot be used in the electrical vehicles at all due to the higher amount of nickel, so the more safety issues. Okay, so this is about NCM materials. Okay, lastly, maybe I simply talk about my research group. We just mainly focus on lithium-rich oxide. This is another kind of materials. This material is quite different. This can be viewed as another kind of layered oxide materials, like NCM materials. But only different is this material has a higher amount of manganese and lithium. But this material suffered terrible voltage decay problems. Even today, this material hasn't been commercialized. Okay, so, there's still a chance to commercialize these materials. Okay, so lastly, I just want to summarize again, for lithium-ion batteries composed of 4 different parts: cathode, anode, electron, and separator. So even your cathode material can get a very good cathode materials, but it should be still has some significant improvement in the electrolyte design, also separator, also anode. Okay, thank you.
Yeah, do you think LCO will be replaced in the 3C products by probably NCM? I noticed some NCM batteries is being used for 3C products. How do you think?
Yeah, partially. Let's be clear, 90% using lithium oxide, partially using NCM materials. That's because the LCO has another advantage. So that's a highest tape density. So that means the volume energy density of the LCO is much, much higher than any other kind of cathode materials. Yeah.
Okay, good to know that. Okay, my question to Jingjing will be applications. She works in a company, I guess she's focused more on application extension, more and more application scenarios to be included. And I also noticed that you mentioned that Great Bay Area is a test bed for different systems. Why test bed? You don't think it's a market? It's more like
because it's a small market.
Small market. Okay. Again, sorry. Yeah, it's.
The
probably Great Bay Area will be okay, but Hong Kong will be small market. That could be an issue. So I would like to know more about again, the evolution of application scenarios for lithium-ion batteries from the beginning to current to future. Yeah.
Yes. For me, I think in the past 20 years, the lithium battery expanding from the consumer electronics to EV and EV power and energy storage, and driving the global green transformation. I think for the tech advances, we know that the energy densities increased from less than 100 to more than 300, and with drops of the cost over more than 90%. Yeah, and for the industry scale, at this moment, China produces more than 60% of global batteries. Yeah.
60%.
Yeah. 16%.
I was quite surprised. I thought it should be 90%.
Yeah. And for the applications, I think it's transformed the just cell phone and the laptops to the EV and energy storage. Yeah. For the future tech directions, I think it will focus on the safety, energy density, and the sustainability. Yeah. Maybe the all solid-state battery is one of the solutions for very high energy density and solving the safety issues at the same time. And for the energy storage, it will be used with more complex systems and allowed the integration of other energy styles, for example, the green energies. And also for the applications, I think it will be in the future, more applications will be seen, for example, in the eVTOLs, for the dynamic power of the eVTOLs, and also the charging for these eVTOLs, and also the on-ship charging for the electric ships and the robots and something like this. And another, I think, is very important improvement in the future is use AI, lasers, and simulations and the digital twin techniques to further smarter manufacturing. And for the recycling, it's also very important in the future to better reuse of the material and to reduce the waste. Yeah.
Okay, thank you. I would like also take this opportunity to thank Jingjing for all this support. She works in companies, and sometimes we need particular support from company a lot of times. So she always been quite supportive. So for Professor Lee, in fact, my question will be about electrolytes. We are having too many types of electrolytes, all organic, sometimes aqueous, and solid, quasi-solid state. And also, it seems that, for example, solid-state electrolytes are quite popular in terms of concepts. But on the other hand, it seems the liquid types of electrolytes is, the progress is more solid, even better than the solid electrolytes to solve the problems. For example, even the safety issues of the lithium batteries, if you use advanced liquid electrolytes, it could be even better than solid ones. Solid electrolyte has many problems. So I would like to ask for, again, the evolution and also the future perspectives for in terms of electrolytes.
All right, thank you. Yeah. Yeah, I have been working on the electrolyte design for past 6 years also. So to answer this question, I think if you are the audience, you are working on the battery, if you know the history of the battery, there's a very interesting history about why we are using, why the emerging of the graphite is like 30 years before it's commercialized. I think the reason is that at that time I can't remember the professor's name, but he chose the wrong solvent. He used for example, the EC over the PC. Therefore, it's really delayed the commercialization of this technique for over 30 years. So then we went back to this, try to commercialize the sodium metal batteries. And then in Canada, there's a company back in the 90s. And then because they put the batteries and put it in the car and on the road, and then catch fire, and they recorded the company when it bankruptcy. Then went back to the lithium-ion battery. So this is the storyline about the electrolyte design and careful electrolyte selection for the graphite, especially for the integration graphite and LCO. I think this work is done by Professor Jeff Dan from Canada. And I talked to him, and from then on, we know that the electrolyte design is really important. So it's only one, again, the ECPC difference is the only one methyl group differences, methyl substitution differences. So I think, but the performance on the graphite is totally different. So now, as you, Professor Chi just mentioned, that there are many developments on the electrolyte point of view, especially on this liquid one, because we have available 1,000 of molecules, right? And then people are working on this area. They try to, a lot of different people are working different subjects try to go into this field and then make a combination with the different available solvents. So in this field, with the help with the artificial intelligence, we really can advance this liquid electrolyte development very fast and very quickly. But for the solid electrolytes, it's really challenging for both the interface connection and among the other questions, and the other issues. So I would say But now we are in a bottleneck that if you are using the existing chemicals, even though we have inventory of over 1,000 and 1,000 chemicals, nobody has found the right chemical to successfully cycle the lithium metal batteries and also the silicon batteries, right? So then people try to combine the material design. For example, Professor Liu Qi did the work for stabilize the high voltage cathode, right? And also Professor Cui Yi from Stanford, they try to nanosize the silicon particles so that they can somehow migrate the volume change. And this morning I just checked the stock value about the Amperis, the stock company built by Professor Cui Yi. And it's very interesting that the market went down to $1, and then today it's about $7 now. So I think this evolution meaning that they must find a way to solve these technical problems, not only about the nano size of the silicon particles, but also about maybe about the electrolytic design. So in my view, I'm a synthetic chemistry. I'm proud to be a synthetic chemistry. So I did some work because I made the combination of my previous coordination chemistry and material science appearance. So I would call, and also my professor, Chen Wang, made the call to the DOE that we really need to develop and find new chemicals for the new batteries, for the new electrode. If we try to find something that already in the pole, in the chemical pole, for existing there for over the 35, 50 years, I think everybody already tried to say anything. So now we really need to the organic synthesis and the material science people to work something out really new from the chemical point of view, from the mechanism point of view. That's my view, and that's what I'm going to build on in my new group, combined with the chemistry department advantage in the Hong Kong U, also with my expertise for the electrochemical storage. Of course, I would like to collaborate with all these professors and the expertise in this area. Thank you. Yeah.
Sure. So I have one common question for all of you at the end of this discussion. In fact, I know that I'm not quite sure if that is correct or not. Even nowadays, lithium battery is so dominating market, but according to what I know, the market share for lithium batteries is around 16%. That means there's another 40% or slightly less than 40% occupied by other batteries. That's typically lead acid battery and nickel metal hydroxide batteries. That's typical aqueous batteries. Yeah. I think lithium battery is not fully, let's say, occupy the market is probably because of safety issues. I noticed that. So, so my question will be to all of you that you feel confident for lithium battery to thoroughly solve its safety issues. That's probably the day the lithium battery can fully occupy the market. You feel confident, or you don't feel it's generally not possible, or well, how do you feel? Just briefly.
Okay, so this is a very challenging question, actually. So because I'm doing research on the lithium-ion batteries, so if I'm confident to fully address the safety issue about the lithium batteries, I don't know how to say. So
how many times you have fire accidents in your lab?
No accident. Yeah, I'm pretty sure because I'm not doing battery assembly. I'm doing material synthesis. So, and as Professor Zhi said, that safety issue is always a big concern for lithium batteries. But I do believe there may be, I think everybody should be here about a solid state battery, right? So, but I do believe solid state battery is a good issue, can solve the safety issue. But I also concerned about all solid state batteries, because for me, maybe okay, don't tell everybody else, okay? So for me, solid state batteries just like absolute zero Kelvin. So you can approach it and you can never reach it. So yeah, so yeah.
So work on aqueous. Good to know that.
Okay. So yeah.
I think there is nothing is zero danger, and so it's depending on the special of the materials. And
So I guess you don't do materials research, so you have this
yes,
confidence.
yes, and I think that because we drive car and we use the gas, the fuels, it's easy to fail. But we have to use it every day. So for the lithium battery, I think when the safety management technique improved, the system's techniques to control it where these problems can be controlled in a very low rate. Yeah, but I think it's not zero.
Yeah. Okay. Good to know that. I mean, please. Yeah.
Thank you for the question, Professor Zhi. I'm 100% sure that the lithium batteries will be safe. Yeah, because I'm a chemist and I work with a lot of chemists, chemistry, and actually we already did some the electronic development try to address this safety issue for the battery. I think the thing is not about a lithium battery. Your question about if the lithium battery is going to be safe, right? I think as long as we are using the electrochemical mechanism for the energy storage, if we want to improve the energy density for one cell, it doesn't matter if it's lithium or sodium or aluminum. If the energy density is higher, there is a possibility that it can catch fire, it can explode, because the energy density per the grams will be exponentially increase. And we need to find a way to control that. And also from the chemical point of view, we know there are a lot of chemicals that are not flammable, right? They are flammable retardant or even strictly non-flammable chemicals. We can develop and try to modify it from that point of view. And also not even mentioning for the solid state. And for the solid state, I want to add one thing for the audience that people, when they introduce the solid state, they address the safety issue. But I have one question. So for the coal, right? For the coal that we burning in the winter, in the older days, try to get heat. Is that solid state? Right? So in that kind of view, that the solid state is flammable, right? It's not strictly like, okay, solid state is not flammable, right? So this is the one argument. But again, if we want to really try to address this safety issue, there are many things we can do from the chemistry point of view. And also, not even mentioning that we can make the battery management from the other side of control. Also see the Gaussian company already have this safety box and everything. So the safety, the safety thing, you will see if it's inside the particle it will burning, or the cell will burning, or the building will burning. So it's a different kind of level. So I would be very confident and to see that it will be safe. Otherwise, we will not have no future for the lithium batteries. Yeah.
Okay, let's hold all of these views for next 20 years. Yeah. When I'm getting older, when you guys getting older, let's see, look back to see what's going to happen. Okay, this is the end of our discussion.
Thank you.
Should we take a photo? Or?
Yes, thank you very much. May I invite our distinguished speakers and moderator to take a group photo, please. And once again, thank you very much for our speakers for sharing their insights on technology and material evolution for energy storage and bring us real-life examples from a commercial perspective as well. May I invite our guests to look at our official camera at the front. Please keep looking at the camera with a thumbs up. Thank you very much. Please be seated. We are now going to have a coffee break. The final session of today's subconference will begin at 4 p.m. See you shortly. Thank you. Hello, everyone. Welcome back. This is the last session of the day, and we will focus on the theme, the future of electrochemical and energy storage. In order to respect and protect our speakers' copyrighted content, we kindly ask you to refrain from taking photos and recordings. The moderator of this section is Professor Shao Minghua, founding member and Honorary Secretary of the Hong Kong Young Academy of Sciences, Chung Yi Chen Professor of Energy Engineering and Environment, Head and Chair Professor at the Department of Chemical and Biological Engineering of the Hong Kong University of Science and Technology. Please welcome Professor Shao.
All right, good afternoon. Thank you for coming to join the third session, the future of chemical energy storage. And we have three distinguished speakers in this session. The first one is Professor Jean-Marie Troscom. Professor Troscom is currently a professor in Collège de France and chair in the chemistry of solid energy. And he is currently a visiting professor at HKUST. So we have the opportunity to invite him to give a talk today. But unfortunately, he had some issue with the ankle, so he cannot come here to deliver the talk in person. Instead, he will give the talk through Zoom. So let's welcome Professor Troscom.
Hey, so do you hear me? Hello? Hello? Hello, good afternoon, everyone. Yes. Okay. Good afternoon, everyone. You hear me? You hear me? You hear me or not? You hear me?
Loud
Good
and clear.
afternoon. Is it okay?
Yes, we can hear you loud and clear. You
Okay,
may
good.
start your presentation. Thank you.
Hey, so good afternoon, everyone. So it's a great pleasure to be part of this symposium, even so I cannot join it directly. But I would like to thank the organizing committee and, of course, the MINOA for inviting me and for giving me the opportunity to talk about a field so important as the one of battery. And today I will try to give you a flavor of the type of research what am I doing. So I will think, even so being Hong Kong or in China, you don't need to be recalled that the batteries are an hour of constant scientific evolution driven by business. And I think it constantly evolves in terms of materials, as you can really have new phases coming, such as high nickel-rich compounds, as well as new phosphate, like lithium manganese phosphate. And at the same time, you have also new technology, such as the solid-state batteries or sodium ions. But also this field is really driven by business. As you can see, the storage capabilities will increase to about 4,200 gigawatt hour in 2030, and this represents a huge business which will double in the next 10 years. So the question is, how do we can keep this momentum? So you need to keep this momentum, you need to realize that the field of batteries is a multidisciplinary scientific field in which you have three pillars that are materials, device, interfaces, and these require a lot of skills in organic polymer chemistry and solid-state chemistry and surface engineering, as well as the development of diagnostic tools in order to know what's going on in the batteries. And of course, this is going to be guided by some kind of theoretical work and so on. So today, of course, I am not going to cover all these topics, but I would like only to focus on some kind of new area that we have been opening in this field. And this will be, in this case, the battery diagnostic. And the question you may ask, why do we want to enter in the private life of batteries? For simple reasons that you need to realize that today, because of this kind of very sophisticated diagnostics, we use the batteries to 70% of the total capacity. Then we like to give a second life to the batteries, And third, and one application that is becoming very important is how to integrate it, the EVs to the grids. And this is more or less what we call V2G. And unfortunately, when you are looking here, once you have sealed the battery, it's becoming a black box. And the question was, how can we enter and know better about this black box? So to do this, I think 7 years ago, we tried to get some inspiration from the field of medical. Indeed, if you go to an hospital for surgery, the surgeon is going to try to get information by really putting optical fiber on your body and get some output. So we want to do exactly the same thing. We want to see if we can really use optical fiber to get information about the lifetime of the batteries and so on. So to a certain extent, the goal was to try to establish the electronic health passport for each batteries. So to do so, we decide to really use optical fibers. Optical fibers that are indicated here are nothing else than the waveguides, the ones that you use for telecommunication, where you have really two parts, the core and the cladding. And we are going to use this kind of single mode optical fiber, where we are going to use only the core. And then we are going to inscribe in this fiber this kind of sensor that we call Bragg grazing sensor, which is FBGs. And the way you do this, you are going to modify over very short distance the refractive index of the fiber. So like that, you are going to have a Bragg grazing that is going to reflect a specific type of light as a specific wavelength. And this is more or less this type of wavelength that you are going to follow by monitoring as function of temperature, pressure, and the strength. So how this stuff works is indicated here. So you take an 18650 and you can put this fiber with these FBGs in the center and on the surface. And here you can really determine what is the gradient temperature between the inside and the outside of the batteries. And you can see this gradient, which is not a surprise, does increase when you are, in this case, using high power. We can also use another advantage, which is multiplexing, where in this case you can put 3 or 4 FBGs in the same fiber, and you can now monitor some temperature gradient along the y-axis. And you can see that now we can obtain really a temperature imaging of the battery using this kind of sensor. So the question is now is how useful this is and what type of information. So indeed, we can really obtain this temperature change, but you really want to know what will be the equivalent in terms of rate and so on. And it's here that we have designed an optical calorimeter, as clearly indicated here, where we are using 3 FBGs, one inside, one at the surface, and one outside. And then we really model the system by, in this case, a zero-dimension thermal model, in which the capacitance represent or feature the heat capacity, and where the resistance feature the inverse of the heat transfer coefficient. And from this, we can deduce simply the heat equation of the battery, where you have the total heat generation, that is the sum of the flow rate plus this term, that is in this case, the specific capacity, which is a cell accumulate heat. And this value is very important to design very efficient EV cooling systems. But what I want to show you here today is to use really another parameter where I am going to do. Sorry. Now, if you look at this heat, this total heat, it can be broken in 3 components. The first one is what I will call QP, which is, in this case, a parasitic reaction, which is more or less the heat associated to the formation of the SAI that is kind of controlling the lifetime of the battery. The second term is electrical losses, as clearly indicated here, and the third term is entropy. So today, we are going to focus only on the first one, that is dealing with SAI. So what type of information can we get on it? As you can see here, when we shine lights into the battery through the optical fiber, we can see the voltage in black of the curve. And then you can see the thermal variation indicated by this kind of yellowish curve, where you see peaks associated to SCI, associated to phase transformation, and so on. And now, to really ensure that we are really measuring the SCI, you know that the SCI is a parasitic reaction that is associated to decomposition products, which at the same time generate gases. So we measure at the same time what will be the change in pressure of the cell. And you can see that indeed, at the time where you form the SCI, where you are triggering this chemical reaction, you have indeed, in this case, a huge amount of gases, an increase, which clearly indicate that we are, in this case, really probing the SCI. So this, more or less, is quite very important because now we have a method in which we can really look at the effect of various additives and try to determine what will be the best SCI. And indeed, this is what we have been doing, namely with the sodium-ion cell, where here you can see the heat associated to the formation of SCI and CEI. And now, when you want to optimize an electrolyte, you can really use different additives and every time monitor what will be the heat generated. And you can see here, where I put in blue the value associated to the SCI means the negative electrode, and in red or orange, the watt to SCI. And you can see we are adding several types of additives. And if you look at number 5, which is more or less a combination that you can see here, this is exactly the kind of electrolyte formulation that we have already developed and is used in today commercial batteries. So this is more or less what you can do in the case of sodium, but you can also do the same thing in the case of lithium. And I will show you here 2 drastic examples in which I will compare 2 types of NMC602, use graphite and on the left, and silicon graphite, 70% in the right. And you can see here the capacity of quartz is twice in the case of silicon. And now we are going to measure what will be the heat generated during these cells. And you can see, for instance, in the case of graphite, you can see the black curve here, where you have heat generation at the beginning of the process, while in the case of silicon, you can see that the SCI generates heat all along the formation. And we can, in this case, also measure pressure. And if you look at the pressure, as you can see here, we have a very weak increase of the pressure in the case of graphite cells, while in the case of silicon graphite, we have a huge pressure. We can reach about 10 bars, and sometimes it can pop up the safety valve. So this clearly indicates that we can definitely determine what is really going on into this type of cell and so on. So, and besides this, also, what we can do means that we can really, in this case, try to determine between temperature, strain, and pressure. And this is more or less what is indicated here, where now we can put really this fiber into jelly roll and put them between different layers, as you can see here. The temperature, and we can also now deconvolute and get the strength epsilon. We could also get this into parcel, as indicated there, and in this case, we can also get, by using this type of cavity, which is a Fabry-Perron cavity, the pressure of this vessel. So this is more or less what the type of physical parameters that we can obtain by optical sensing. Now, at this stage, what I show you is more or less the way that we can form these different type of parameters, physical and so on. But what we like to do is really to have access now to the chemistry of this battery and the different type of species. So we want to do so, we are going to modify our sensor, and by daily, in this case, trying to probe or to spy the alignment of the fibers. And to do so, we are going to tilt our grating so that some light will escape daily in the cladding mode. And by doing so, we are able daily to probe some kind of change, namely refractive index of the environment. And this is more or less what we can do. You see that now, of course, the spectra is quite more complicated because you have at the very high wavelength the black resonance, and then you have the cladding resonance where you can find the sensing mode as indicated by the asterisks here. And what is very interesting, you can take electrolyte and you can change the amount of lithium, and we can monitor the variation of refractive index, which is of the wavelength and so on. So this is more or less what we have developed And I'm going to show you how we can use this stuff in real practical batteries. And I will take or go back to the case of this kind of daily NMC silicon graphite. And you know that in these batteries, we have a 75% of silicon, which means that the volume is going to expand by more than 200%. So when you are going to format the cell, you are going to have variation of the volume within the cell. So to do this stuff, we try really to understand what's going on here. And what we have done here, we have really used this kind of TFBG, and we put 3 TFBGs and rows as indicated here. And like that, we are going to monitor what is happening through the cell in terms of the level of electrolyte and in terms of the salt concentration. And to do so, we are going to do this kind of experiment where now, as you can see, when I charge my cell, you can see here, I really look the variation of potential and look the answer of TFBGs that are on the right. And you can see, I know at which level my electrolyte is and so on. So you go up, and then after on discharge, you are going to see the same thing. The top sensor is going to be, in this case, moving down. Okay, so you're going to come in soon. Yes, and then after you see it's going back and so on. So these are the ways, more or less, that we can now control what's going on into the batteries, on seal, and to this type of silicon technology. So from this now, we can really analyze the data and determine what is the change in the refractive index as function of cycling. And you can see here, you can see the lithium-ion concentration is kind of changing quite a lot during the cycling of the cells, where we have around about 30% of change in the concentration gradient. So this, again, and told you that we can really spy what's going on into this type of batteries in terms of level of electrolyte and gradient concentration of lithium. So this was the first part toward understanding the nature of the species. And the last part that we have been pursuing is indicated here, where now we really want not only to have an idea, we really want to know what is really the chemical formula of this kind of parasitic species. So in this case, we really pursue the track of evanescent waves, and we try to get or enlarge the evanescent waves. To a certain extent, we have done nothing else that do microscopy, but with now an optical fiber. But of course, if you want to do with an optical fiber, we have issues. Because if you look at IR spectroscopy, you are looking at vibrations or molecules that vibrated in the range of 0.3 to 13, 14 microns. While if you lose the silica fiber, they are not transparent within this range of wavelengths. So in this case, we are obliged to overcome this puzzle, and to do so, we have really changed the type of fiber that we have been using, and we have moved from silica fiber to telluride fiber. And by doing so, as you can see here, we can now place the fiber within the batteries and collect the infrared spectra with a very nice resolution and so on. And this enables you to have access to a lot of observable within the batteries. As you can see here, we can now look what is happening in terms of electrolyte decomposition. We can also look now, determine the molecules that are being solvated or non-solvated by the lithium, and we can even have access to the insertion process and the positive electrode as indicated here. Excuse me. So let me give you an example of what's going on. So this is more or less a classical example where I am going to try very simply to see what is the purpose of adding an additive to the electrolyte. And I will add here the most known additive, which is vanillin carbonate. And as you can see in the spectra here, I am going to look at the absorbance of the carbonyl group. So to do the experiment, I will place the cell here, where you see the voltage at the top. Then in the middle, you see the variation of temperature, which means that I have nearly a classical fiber inside. and I can really detect, as I mentioned to you before, the SCI by this kind of nice peak. And then if I now monitor the absorbance of this carbonyl group, I can see the carbonyl group absorbance remain constant and just start to decrease when I trigger the SCI formations, which means when, in this case, I decompose VC. And of course, this ends up as a first cycle, and this is not coming. So this is really a powerful method in order to understand what's going on in terms of additives and at which potential they can be triggered when really you are doing this type of action. So this is a kind of 1850, but you can do now in the case of general batteries, and this is a case where I show you, where in this case we put a fiber and a pouch cell, and we are going to monitor as indicator, sorry again, the variation of the infrared. And you can see we put the fire in there, you collect the data. Excuse me, because I have a throw again. I will drink. And in this case, what you can see that you daily detect by difference the different type of species, and we can determine what are the organic components like lithium ethylene dicarbonate, LEDC, inorganic component lithium carbonate, and even in this case, dimethyl dioxohexane carboxylate, DMODHC. So you can see now we have access at all the chemicals that are going really to participate to the SCI formations. But the question is it really the soluble part of the SCI, or is it really the solid part, means have you really crystallized the SCI? So to do so, what we have been doing is really take a cell and which we put down the fibers at a different position within the cell. And you can see that now, when the fiber is really along the graphite, you have a very large intensity of the species, while when it's far away, you have in this case less species. So which means in this case, you have a kind of diffusion with some of these species recrystallizing. So the question is, can we see now this nucleation process? And indeed, when you really measure this and really do chemical concentration of this species, we can see that at the beginning, we have really a huge increase in the species in solution, and you reach a saturation point where you have nucleation. And at this stage of nucleation is where you are really, in this case, growing your SCI, your solid SCIs, and so on. So this is more or less the type of information that we can get. So the question you may ask is, how useful is it to do this? How useful? I will try to emphasize here, because now you can really establish some formation protocols, and you can see here some curves showing you, again, the variation of the absorbance, which means the nucleation growth, depending on the electrolyte amount, depending on the cell rate, depending on the temperature. And these information are very important in order to determine the formation cycle of your batteries. And you can see that knowing the information, we can have now access to what will be the lifetime of the batteries, depending on the type of protocol you are going to set up for doing this kind of daily formation cycle. So this is more or less what you can do with this type of sensing. Then you can even go one step further. And one step further is some work that we have been doing just recently, where now the question was, can we really couple the electrochemical behavior together with optical sensing? Which means that can we have a synergy between the two types of measurements, and can we measure at the same time the electrochemical driven process and the optical sensing? And to do so, of course, you want to use a fiber as a working electrode. So you want to use as a working electrode, you're obliged, of course, to have electrons, and you're obliged to do a metallic coating. And in this case, this metallic coating has to be really not absorbing the infrared, which is on white. What we could not use in this case, gold, we are obliged to use ITO, a transparent conducting oxide. And by using a transparent conducting oxide, now what we can do, we can really monitor the variation of the infrared spectra as function of the deposition of the materials, and as well as function of the intercalation. And as a proof of concept, I will show you this on the case of Prussian blue, where in one point here, what you are looking, we are nearly depositing Prussian blue into the fiber, and we can see the absorbance that does increase at the bottom to level up, which means in this case we know the thickness of the deposit, and then after we can nearly move this non-aqueous electrolyte, and we can nearly do the electrochemistry, and as you can see, we can monitor the CN band, and we have a complete idea about what is going on in terms of processes and so on. So this, what you can do, now you can really improve all these kind of things, and this is more or less what I show you so far. We can really use FPG, we can really tilt the FPG, and we can then put kind of, in this case, of coating on this fiber. And of course, last part is we can also put coating on the TFPGs. And if you put coating on the TFPGs, in this case, we are going really to trigger the surface plasmon resonance. So what you are looking here at the top is a classical TFPG with a cladding mode resonance. Now, if you take a metallic coating at the top of it, you are going to have really a collective vibration of the electron at the surface of these coatings. And when, in this case, the frequency of this collective motion of the electron at the surface of your gold will be really equal to the frequency of the light that you send to the fiber, you are going to what we have here, we transmit energy from the light of the fiber to the collective mode, and you have this kind of dip, which we call the SPR resonance. And this, we are going to use it really to look at very tiny electrochemical process, because by doing so, we increase considerably the sensitivity of the fiber. And indeed, this is a typical measurement that we are doing, where you can see here, again, the counter electrode, the working electrode, a very simple electrochemistry, and we are going to monitor all this. And this is more or less what you can obtain in the case of Prussian blue, where you can see very nicely the two signals and so on. And this enables you to get very high sensitivity, so that now we can even look at the double layers and all these kind of supercapacitor and so on. So this more or less, in this case, this open, I will say, a new field of exploration and really kind of fancy electrochemistry and so on. So at this stage, I try to kind of summarize a little what I show you. This is more or less an activity that we start about 6-7 years ago, and I show you that we can really determine the temperature and the pressure. We can have access to the thermodynamic values. We can have access to the strength. We can have access to turbidity, refractive index. And I think the highlight of this is that by now we can have really access to the famous SCI that is controlling the lifetime of the batteries. So of course, the question is, how this is useful and how this can benefit our battery manufacturer and so on. So indeed, this is more or less what we are looking now, where we try to implement this stuff in the field. Of course, we are not going to use the fiber and put the fiber in each set, but we are going to use the fiber as a snake that is going to really propagate through the module. And here we can really determine in each cell outside the temperature of the strength. And if you do so, we have already demonstrated in sodium-ion cell, where you can see here the variation of the capacity as a function of cycling, and we can monitor here both the temperature in the middle, and you can see in agreement with a very good capacity retention, there is not too much change, and you can see here the strength. And what is very interesting in the strength is that you have a two-slope, and this two-slope reflect exactly the breathing of the positive electron material upon uptake or release of sodium. So this is more or less what we can do. And this is more or less, I will say, a study that we have been pursuing with Professor Tam from PolyU, which is an expert on optical fiber. And this project, I think by now, is really involved a wide range of industrial sectors and a lot of international collaborations. So to conclude it, during this presentation, I hope that I convince you that now the battery is not any longer a black box. Because the sensor, we can now have access to the thermodynamic parameters forming the SCI, means the physical, delta H, delta S, and so on, but also all the chemical species involved in the formation of SCI. When I say all chemical, of course, the ones that are active by infrared, means that the species like lithium oxide or lithium fluoride cannot be detected. And then, if you look now at the applied level, our dream is really the one that we can really integrate this stuff and EVs. But of course, we are very far to this because we have really a lot of bottleneck. And I think we need to have a very huge interaction with other type of field. And again, the multidisciplinarity that I mentioned to you now is also becoming very important in terms of applied research. And with this, I would like to thank you for your attention and thank you all the people that have been contributing to this work. And again, thank you for your attention.
Well, let's thank Professor Troscom's very intriguing talk about using the optical sensor to monitor the status of the battery. We can do the inside and the outside measuring what's going on with the batteries. Okay, so I continue. The second. Okay, and our second speaker will be Dr. Gong Jiadong. Okay, so Jiadong. So Dr. Gong is the Vice President and also the Chief Technology Officer of the CITL's International R&D Center in Hong Kong. So he is the expert in the AI area, and he will give the talk about this, how to actually do the innovation with the new, the era of the AI. Let's welcome Dr. Gong. Thank you, Dr. Gomes. Very exciting talk about the development of CATL and also the application of AI in the material and also other kinds of innovations. Let's thank Dr. Gong again. Our next speaker is Professor Chen Guohua from the HKUST. We actually from the same department. Actually, Professor actually hired me when he was the department head at HKUST, and he moved on to PolyU and the CTU. Then this year, finally came back to HKUST. So Professor is an expert in the lithium battery, so he will talk about the energy storage opportunity and the challenge. So let's welcome Professor Chen.
Thank you, Minhua. So very happy today to give this talk. When Minhua asked me whether or not I can give a talk here, I thought I'm not young anymore. If I talk, because we have so many young people from different subjects, so maybe I talk something in general. And today I realize I'm the only one wearing a tie. Anybody knows, not you, huh? Anybody knows where this tie belongs to? No. This is Hong Kong Academy of Engineering. Okay? So I wish some of you, when you get, a little bit older, okay? So incubated from this young academy and then become a member of Hong Kong Academy of Engineering or Science, okay? For the electrochemical energy storage, so today you have heard quite a number of people talking about it. And some from technical point of view, and just now Dr. Gong gave quite a comprehensive introduction. So I will just go through my slides and with some numbers, so that hopefully you can take some message home, saying that at least we still have lots of challenges to overcome and many opportunities to make name or money. Okay, so, well, why we do energy storage, electrochemical, whatsoever? This is the root, because now we are having a burning or warming Earth because of the consumption of fossil fuel. And you heard about zero carbon or reduced carbon emission. All that is to try to reduce the temperature increase. Last year was the hottest year in our recorded history, and the year before was the highest. What does that mean? Means that in the past few years, our temperature on Earth increases continuously. So in terms of this value, so on land, the increase is over 2.28 degrees C comparison with the average of this 1951 and 1980. So that's sort of early industrial period of time. And for ocean increase, it's already over 1.15. So Paris Agreement. So we want to control the temperature increase of the Earth that is below 1.5 degrees C compared with the pre-industry level. So looks like we have a very tough job to do. So I'm very happy to see, we have so many researchers, professors, and the industry committed to this. So hopefully we could bring this down after some years, because 1.5 degrees C, what we talk about is by the end of this century. Okay. And so for the globally with greenhouse gas emission, the contributor largely is from energy production. So that's why we're talking about energy. And so because energy is directly related to our economy, and so the growth of population and also prosperity leads to the not only that the per capita increase of the energy, but also the total amount. And for the electricity, we're talking about how much, and here you see this bar is China. So we are number one. So in terms of consumption, it's close to 9,000 terawatt hour. And so that, so it's double that of the USA, and of course much higher than the third one, India. This is about 1,500, okay, terawatt hour, okay? So China has lots of demand for energy, and this energy, electricity, basically, so we're talking about is, most of that is from coal burning, and a little bit natural gas and oil, and after that, the renewable part, so, and nuclear, so in China. So this is good news that we have in 2024. The portion for renewables is quite big. And the renewable, of course, that requires energy storage, because renewable has the mismatch of the time between demand and the supply. And another thing we're talking about also, that is the grid load leveling. And well, this one gives the trend for the CO2 emission for China. This is, well, in this comparison, the only one increasing because of our economic development. And so now we share, so over 1/3 of the total CO2 emission. Okay, so we have lots of things to do to clean up, and also our responsibility to do so. And this one, when we're talking about the renewable before, see the addition of power generation in 2024. So we're talking about the increase. So over, 2/3 of the additional generation of power in China that in last year. So that is renewable. That is good, okay? And among them, we have solar generation, wind generation, and also some hydro, okay? So that's the good news. And also that needs energy storage. And you can see that this is the yearly installation for energy storage capacity from America, from China, including the Asia-Pacific, oceanic area, and Europe. What you can see here, so China, this red bar, this part, please, this is over 1/3 of the world total. And globally, we're talking about cumulative capacity. By 2030, we are talking about the installation of energy storage capacity over 500 gigawatt. And So close to 3 hours operation, you're talking about that will be this 143.2 gigawatt hour. That is the energy capacity, okay? And what are the technologies we can use and for the energy storage and the time of the storage? So depends on the technology we talk about. Supercapacitor that can store so very short period of time, for example, below minutes. Okay. However, it can deliver quite high power. We're talking about 10 megawatts, that kind of level. And for such kind of device, and this, so is this one means we're talking about early commercial. And this is not largely used or has not been fully commercialized because of the expensive materials, basically high quality active carbon. So if you know how to make high quality active carbon and also use biomass that is abundantly available, then you could make this commercially viable. So that is this one. And another one we're talking about, that is the mechanical energy storage, flywheel storage. Similarly, it has a short time for the storage, but it can, depends on your design, can deliver from 100 kilowatt to 100 megawatt type of power. And when we're talking about batteries, you see batteries depends on the type of battery. It can be utilized from minutes to few hours. And most of our now the battery installation for energy storage from the grid, we're talking about 2 hours to 4 hours time for the energy storage. And we're talking about lithium ion here, fully commercialized. You have seen that talking about from Goshen High Tech, from CATL. So they have been selling or prepared to sell more lithium-ion battery. And the next one we're talking about, that is sodium related. And this one is sodium sulfur lead acid, and they commercialized available, but in terms of installation, so they're not as much as this one. We'll have a slide to show later about this. And here we're talking about also batteries using aqueous electrolyte. And so this, so in the demonstration period of time, and if we could improve its circling stability and reduce the price, of course, that would have also potential. And the flow battery could store the energy for a few days. And because it can deliver a reasonable amount of power, and this one is in the demonstration stage. And the reason it's not largely adapted because of the cost. And this cost of the electrolyte and the cost of the membrane that maintain the efficiency, so that would determine factor for the future application of this one. And the others, chemical like using machine hydrogen or the ammonia, that could give seasonal or days or weeks energy storage, and depends on the capacity, it can vary a lot for the power. However, so they are not commercially available yet, and lots of research going on with that. And of course, this one we're talking about pumped hydro has been used for many years, and because the facility that requires that if you have a power generator from the hydro energy, then you could use such kind of option. Otherwise, install such kind of facility is very expensive. And some are mechanical, so that's some research going on, and some in the early commercial, for example, compressed air energy storage. Okay. And talking about electrochemical energy, and in China last year, we has cumulatively reached nearly 140 gigawatt for energy storage. And among that, so lithium-ion battery is 76 gigawatt, and the remaining, that is 58.5 plus a very small amount of other type of energy storage. Okay. And why lithium-ion battery has been now the major player in the energy storage? And this figure, I think, properly tells that we should congratulate to ourselves those working on the perfection of lithium-ion battery. Not only we heard from Dr. Gong that we have the safety from ppm, ppb, but also for the price-wise. In the past 10 years, the price dropped from over $800 per pack to now this year. Well, this is the from Bloomberg from their survey. So this is about $115. I think in China, probably you agree with me. Now in China, this value is already below $100 US. So of course, such kind of decrease of the cost, not only from the materials, but also from the perfection of manufacturing, so that you have the high quality of the production of the products. And so competition, again, also. I heard that in China, we have over 100 lithium-ion battery producers. Some would be there just, be a competitor to make sure that big companies reduce the price so that, the market could work better. So this, when I had conference in the US 10 years ago, we're talking about such kind of value, the price. At the time, people say, we dream that someday we would have the cost below $100 US per kilowatt hour. And now that dream is no longer a dream, so it's a reality. And I think the price is still, there is room to reduce, okay? And, well, you heard from Professor Liu Qi talking about the importance of the cathode material. Indeed, the cathode material that is very important to determine the capacity, and also later on you see associated with the important factor that is safety. And here, for 3 regions, China, EU, and also the rest of the world, you can see that you know, the share of the electric vehicle sales by battery chemistry in China, now from 22 to 24, the share of the high nickel or low nickel means that the NCM, okay, so that is reduced from nearly 40 to slightly over 20, and the large portion of that is occupied by lithium ferrous phosphate. And Europe, so they still have a large amount of NCM, and with the big portion using high nickel content NCM. High nickel content NCM means that the nickel is over 50%. We're talking about 622, 811, something like that. And LFP is still not that big. Okay. And for the capacity of EV sales by chemistry from the past 3 years, 21 to 23, you see the similar trend. China, so that is increasing for the LFP and decreasing in terms of percentage of the NCM. Okay. And what is the total or overall trend for the development for the LFP or NMC or NCM? And this is data from the Fraunhofer Research Institute to give the analysis about NMC and also LFP from different countries. We're talking about here, this is for Europe, and this is for China, and that is for Japan, and this one is for Korea, and this is for USA. So what you can see that is, the predicting from 2020 to 2030, we're talking about NMC. So Europe will increase, but China, in terms of NMC selling, so will be decreasing in terms of percentage. And the total amount for the selling by 2030, we're talking about that is 3.5 terawatt hour, okay? And LFP, so China is the major player there, although that Europe so may come in as time goes towards 2030, okay? And by the end of 2030, we're talking about 2.5 terawatt hour kind of ceiling, okay? And so the share of manufacturing capacities, so that we're talking about who is making such kind of battery. What you can see that, the currently installed and 2030 kind of capacity announced, China, so that is the major player for, of course, for China. And for the European Union region, China would be much increasing from below 10% to close to 40% by 2030. Okay, and what the competitor for us is Korea, of course, plus Japan. Okay, and when we're talking about the cathode material, of course, the market now available that FFP, NMC. What are the other materials we're talking about. In fact, there's also some other materials talking about lithium-rich layered oxide, and also high voltage spinel, and also we're talking about that high voltage polyanic compounds like IFP. And this figure B compares their performance in terms of cost, voltage, safety, cyclability, power, and energy density. And for different type of materials, you can see that, for example, this one, so the cyclability or stability, safety, and power, and cost, and all that is inferior to that. And for this one, high voltage spinel, cyclability, energy density, and the cost, that's a problem. And this one, of course, energy density and power density is a concern. So if we want to improve such kind of batteries, okay, so we need to improve here, 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 and here, there, and here, here. And for this one, of course, reduce the cost, okay? And, well, so what are the future, what are the trends in the electric car market? So this one you can see that in the past 10 years, so from very few to now, we're talking about this in total, so that is close to, over 17 million. So yearly is car sale, okay? And China plays a very big amount role here is over half of the car that is sold in the market, okay? And when we talking about energy storage, and why I also talk about cars, because in future, stationary storage with the power generation or grid would not be the major players for energy storage, because with the increasing amount of EV available, how increasing we talking about? By 2050, in China, for example, we are talking about 350 to 400 million cars. And if we assume that, well, by that time we have 400 million cars, EV, and each one has a 60 kilowatt hour on average with this kind of battery, and so there will be 24 billion kilowatt hour electricity stored in EV. And what is this figure? This figure is equivalent to the daily electricity consumption. So it means that if we do not make better use of those EV with the grid, we would not be able to satisfy the EV and also the energy demand from other sectors, industry, and also buildings whatsoever, okay? So if we have the driving range considered, EV can participate grid distribution at a value of 10 billion kilowatt daily. So this is a huge number we're talking about. And so with that, so that it has, EVs will have a capacity to support grid at about 3 billion kilowatt, about 50% of the total national power from the non-fossil fuels or renewables, okay? So this, in future, V2G is an option and has to be properly used. So I saw that your Goshan, you have the Navy cells for the energy storage, and there, so you have the BEE and also some other flexibility. and in future, probably consider with this, and I think it will be good demo, okay? And we're talking about the future smart energy storage. So the car would be participating in the energy storage, okay? And it's not only that. So recently, we're talking about low altitude economy. So that driving the future industry in Hong Kong and also in the region. And by 2030, we're talking about the business for the drone itself projected close to $130 billion. So, and what that means that we need the energy density and power density much higher than today's lithium-ion battery, okay? And so one possibility may be lithium sulfur or lithium air. So during lunchtime, we were talking about this. CATL set a target of 1,000 watt-hour per kilogram. But I think to satisfy this low altitude economy, probably 700 would be enough. But 1,000, of course, that would be even better. Okay. Well, this one is a picture that at Moss Landing, California, used to be the largest energy storage site. But earlier this year, it caused fire. And because of that, and raised lots of concerns for the lithium-ion battery energy storage. Even though now the installation we're talking about, so the number of incidents per 1 gigawatt hour, so the installation, this is small. However, when the fire comes out or the news goes out, either from storage or from the EV, it is always give us a concern about safety. And this is the EPRI USA survey of the battery incidents for the 10 years time, 2010 and 2021. And what you can see here, of course, most of the batteries with the incidents are from NCM or lithium metal. And of course, China is there, but most of those incidents are from the manufacturing by Korea. So it's not only Korean that may not do the good job. I think mainly is because of this chemistry. It's not only the cathode material, but also the thermite we're talking about. Safety is the current collector, the cathode, the anode, electrolyte, all plays a role here. And so because of that, and China has announced this GB 38031-2025 effective next year. So this probably, I think this is the toughest requirement for safety. Okay, so if the battery cannot meet this GB, and probably they could be driven out of the market. Okay, so let me quickly conclude. Electrochemical energy storage has huge potential, and that potential has many years to come. So, stationary energy storage demands low price, long stability of the batteries, and the EV with high capacity battery will replace those ICE-based vehicles. That's the trend. And EV will support grid for power regulation in future through V2G. And then we're talking about the low altitude economy. that demands very high energy density and also power density battery. And safety is the top consideration for any battery to gain the market or to be in the market. Okay. So with that, I thank you for your attention. Okay.
Thank you very much, Professor Chen, for the insightful presentation. Please remain on stage. It's now time for the panel discussion. May I invite Professor Shao and Dr. Gong to proceed to the stage to join the panel discussion. They will have further discussion on the future of electrochemical energy storage. And for our audience, there will be a Q&A session towards the end of the panel discussion, and you're welcome to raise the question. Now, may I pass the time to Professor Shao, please.
Okay, right, please, sit. Okay, so you two sit here, I'll sit here, okay. No problem. Okay. Okay, since Professor Jean-Marie Trascon cannot join us, so we have two speakers in the panel discussion. So as the MC mentioned that I will first ask a couple of questions, and then I will open the floor to our audience. Okay. So the first question that I have is that we all know that China now is leading the energy storage, especially the battery technologies and the manufacturing, of course, right? And even in research and development, I believe. Okay. So my question is that how do we actually try to keep our leading position, right? So we all know that we are facing competitions, from all the world, especially we have Dr. Gong from the industry and Professor Chen from the academia, and I believe that's two representatives to to share to our audience how to actually keep our leading position in terms of the R&D and also manufacturing, right?
Okay. I think that Dr. Gong is the right person to answer this question because your company is the leader in the world, #1. As not only #1, but #1 by large. Well, I would say that the #2 is maybe less than 1/3 of your capacity. So you are absolutely #1. So how can you keep the leading position?
I thought you were supposed to answer the question. I can just throw my 2 cents here. First of all, I think it's very challenging. Actually, there's no guarantee because everybody is thinking very hard on every aspect. From the electrolytes, from the cathode, the materials, new systems, energy storage systems, not just electrochemical systems, right? So for anything that can store store energy. For us, I think that the answer is very clear, right? There's no guarantee. You always have this sense of urgency. If you are #1 in the race, you actually don't have time to look back. Yeah, unless you are Bolt, right? Usain Bolt. But I think we are more competing with ourselves right now. We're trying to see, okay, this is what we can do as of now. What can we do next? Like what I mentioned in my presentation. What can we push the limit? To what extent? Like we discussed, quite lightly over the lunch. I threw out 1,000. The number is a little bit shocking.
That's a dream number.
Yeah, but
maybe 10 years later, we will
without dream,
that,
there's no point for us being here, right? There's no need to set it. Well, that's why we are setting up this international R&D center in here, right? In Hong Kong, working closely with the respected universities, researchers, actually over the world, not just here in Hong Kong. I think it really takes much more than just a company. Takes the whole community to working really close together because there are many fundamental scientific issues, problems. Like when I first joined the company, I was joking, wow, it's really amazing you guys actually figure this out. And some of the answer is just, well, we cannot really say we figured it out, because it's working, but we might not know why. It's just due to our I think there's one thing why China is dominating is because Chinese people is really, really diligent, hardworking, painstaking. If it's one experiment is not enough, let's do 100. If one research is not enough, let's working with 100 researchers.
Well, you have over 5,000, right?
We have more than 20,000 research. So really, it's about pushing very quickly because it's very rapidly growing market in the last 10 years. I think nobody or someone visionary enough see the trend, but most people are not seeing actually how electric vehicles and the electrification has become so rapid in the last 10 decades, right? Those who have saw it must have bought our stock and becomes very rich. The thing is, the industry has grown so rapid. There are still a lot of fundamental understanding, is still not so solid. It still takes a lot of time to examine why LFP works in this way. Like this Professor Li and Liu, and it takes more than just looking at one single material, looking at the characterization. It's actually the interfacing, the interaction with the system. Takes a lot of research from many disciplines. So I think to keep up or to stay in the far front, you have to keep working with researchers over the world from different disciplines and working together to push the limit and trying to get a solid scientific understanding. Even I was talking about, our research institute, the theme is AI for science, but the focus is science.
Yes.
Without the science, it's AI for blank. So I think that's my answer to your question.
Great. Chen, do you have any?
I think I agree with Dr. Kuhn very much, and you want to keep leading position, you have to have the leading products, technologies, and meanwhile, also have to have supporting or that is encouraging the political or international relationship. So this, of course, is beyond the company. So we all strive for peace and cooperation. So hopefully that whoever we meet, we talk about this, we promote this, and then the company can have good environment to make the good products and of course keep your leading position. Okay.
All right, yeah. Great. So it's I think I add one more thing. Probably is the tenant training, right? Because I think the tenant pool is very important for any kind of high technology development. So I'm glad that we have a lot of good students, right? Try to come into this area. We have professors here, and each professor have a big group to train our PhD students. Okay. My second question is really the more technical. So for the next generation of these batteries, right, lithium-based batteries, so everyone is talking about solid state, and actually have been talking about this for many years, right? So what do you think that in reality, when it will become solid state battery dominate years? Okay, so I mean in 5 years or 10 years or even like maybe 20 years. So can you project from now, right? Not because everyone actually already projected maybe 20 years ago. We already, maybe in 5 years we mass produce this solid state battery, but still we are in the process. But do you think that in short period that we can switch from the traditional lithium battery to solid state?
Yeah.
Want to go first?
I'll go first. Well, this question was sort of touched upon before the break. During that panel, Professor Lee touched up a little bit about it, not elaborate in details. And solid-state battery, if you have the solid electrolyte very well made, and also the interface with the cathode and the anode good, and also the conductivity is very well maintained, and the manufacturing could be easy, and also you don't need external pressure or do not need that much external pressure to keep it working. So all that is technical. Then everybody loves solid state because for 1,000 watt-hour per kilogram, I think that has to be solid state, because without getting rid of those solvents, it's difficult to increase the energy density. So this solid electrolyte part, I think many people claim they have done some good work and even patent certain kind of way of making the solid electrolyte, but the market seems to not give them the go-ahead light. So I cannot predict when, but with the collective efforts internationally, and I think the time should not be too long, maybe 5 years or 10 years, or gradually you have small amount, and then after a few years of trial and people start to accept such kind of product, maybe after 5 or 10 years, you will see more solid electrolyte batteries. Okay.
Well, first of all, don't quote me on this, this answer. And this is purely my personal perspective, not reflecting on the company's position. But I think if anyone are familiar with this field and following the news, you heard about solid-state batteries, all solid-state batteries every other week or something. There's a new startup or there's a new headline or blah, blah, blah. We'll have the solid state even by the year end of 2025 or something. Yeah. I think technically, actually, I'm more optimistic. As a people who are working on the R&D, I think if the issue is if you're not optimistic, you will be suffering very much. To be a researcher, you really have to stay upbeat. No matter how big the challenge is, and I think also the reality is, looking into the papers coming out in the last year or so, you will feel actually quite okay. It actually looks like a lot of big progress has been made. So if I won't be surprised if something happened the next year, someone has really actually achieved this full solid state battery and it's been made out and passed all kinds of testing. People, whatever they do, penetration test or even light it up. However, I think what really matters is where's the finish line, because we're not talking when we talk beyond academic, when we talk beyond the lab scale, that's the question. Why I dedicated a lot of content of my talk on quality, on safety, because when we're talking about actual product, commercialized product to the customers, we use the term of TRL levels, technology readiness levels. From 1 to 3 is lab scales, and I think our chairman and CEO mentioned, okay, currently I think the industry is about like TRL level 4, if 9 and 10 is full maturity. Yeah. So they might be seeing something that is fully functioning, everything seems like fine, by next year, but to us, because we're talking about a million repetitions, billion repetitions and parts out there, and if any single one happened, it's gonna be a huge lawsuit and burn the whole business down. So we have to make sure it's not just, oh, we made one, it's working, to actually we made a billion and they all working. Yeah. So that's the finish line we're talking about. So to get there, I think.
Yeah. So maybe just a follow-up question. From the one that is working to millions that is working, so how many years would take industry to do that?
I think, just for lithium-ion batteries, it takes about like 10 years, right? So from the, lithium ferrophosphates.
I see.
And currently, I'm optimistic that can be greatly reduced, at least in half. I think that's the dream. So I'm more staying alert to you guys. Once when you guys have something big and we know, okay, it's coming. Maybe it's just a little years.
So if we give you something that is working, so it will be 5 years later to see it in the product line.
Maybe when we hear it like 10 times, not just the first time, maybe 10 times.
Yeah.
Later, working. It's still actually this one really works.
Yeah.
Right. Yeah. So let's look forward to that. Okay. So all right. So I finished my questions. So let's open floor. Any questions from the audience you want to ask the panel members?
Yeah.
So in terms of AI, so in CATL, what kind of AI is being used to produce values currently? I mean, AI for materials, if you cannot find a useful materials, doesn't count to this. What kind of AI is being used? And for example, in coming 3, 4, 5 years, so what kind of AI you think it could be used for?
That's a good question, Professor Zhu. Actually, I think we talked about a little bit of, over the lunch as well. AI is pretty big concept right now. I'm a material scientist by training. We've been doing a lot. 10 years before, we were calling it computational material science, computational materials engineering, and ICME, or there we're talking about materials genome, big data, machine learning, then neural networks. Now everything is called AI. I think as of now, every single technique of those pre-mentioned techniques still be very useful. Like a lot of things are still on the machine learning level, for general property predictions. But I can see more neural networks and deep learning has been used, for trying to finding the linkage between structures, properties, or all the way from the chemistry to specific structure, then to predict the properties. And I mentioned a little bit in my talk, actually currently you really cannot ignore LLMs and the other. We used a lot of Gen AI techniques, from diffusion models to trying to, there are a lot of open research on this field as well, and using diffusion models to generate new molecules, new crystals.
You in the research area,
yeah.
Research stage, right? I mean, any being used to produce values with that produce something really useful.
You're talking about a new material coming out or a new.
Anything.
Yeah.
One. I guess it's quite difficult.
Yes, it is. One thing that I can share actually is been working right now is, for example, in the electrolytes is a very complicated system, right? Is usually hard for traditional computation. Usually, you just compute the properties of a single molecule itself, or at least the solvation structure or some of the interface is getting hard. So how to get to the understanding the whole system, the whole electrolyte system with multi-component, maybe more than 10 component electrolyte, different solvents, salt additives. The additives itself can be 6, 7, 9. And also, when you add in the interface between the cathode and the anode, it's becoming too complicated for any model or simulation to do. So that's what we did for using AI to come, trying to bridge the gap and trying to design a better, you can do a better combination, a better recipe, or actually by combining the Gen AI, you can try to generate a new additive, which is good, to then solving some of the problems that we are really interested. For example, have a better film formation that can really elongate the life. I think that's something as a very typical example.
Do you have one, at least one material is being designed by AI? How are used in the
Not in use, but we have designed more than one material or molecules so far. Again, we established our research institute is established by the year end last year, right? So there are already things that is coming out, and as I think they are moving up from TRL 2, 3, and 4 stages. They are probably examining them to incorporate it into the next version or next generation that should be rolled out, next year or so. But this is, I think this is it's going to be an evolving iteration. It won't have, beginning, end. That's it. It will have several iterations, until we actually finally get the product out. But right now, I think it's still on the pipeline. It's pretty promising.
Yeah, maybe I just add a little bit, because I know that I share your concern about the overstating of AI's ability. However, if we can make good use of AI, indeed we could save lots of effort. For example, I have a PhD student who is now working on the high entropy material selection. And high entropy, we were talking about 5 or more elements, and the combination of them in different kind of composition. And he chose the most likely number of the elements. If without AI, so we need to do experiments about 250,000 kind of combination. But he used machine learning and compare with DFT values and reduce that number to less than 1,000. And from less than 1,000, we further refine our criteria. Now he has successfully synthesized 20 of such material. So that is something, indeed, it can be helpful.
Okay, maybe one more quick question. Anyone? Okay.
So can I have 3 questions?
For you,
oh, sorry. Yeah, very, very fast. Actually, I have been thinking to do without electricity. Something like kinetically, we can use pneumodynamic. Pneumodynamic, we have not go into that area yet. Okay. And the second question is energy harvester. So with the cloud center, we can harvest the energy from those areas. Yeah. And the third one is about the environmental. I know hydrogen energy produce water, right? H2O. So would that be the reason why we have so much rainstorm recently? I think other energy center, other clean energy, renewable energy also produce water vapor. Is that right? Am I right? I don't know. But I know hydrogen energy really produce water vapor. So I'm concerned whether that is the reason for the rainstorm. Yeah,
okay.
That's my question.
Well, maybe let me answer that, because I used to work in the field of environmental engineering, and I also worked in School of Energy and the Environment. In terms of frequency of this thunderstorm, so that is closely related to climate change. Because of that, we have more frequency of extreme weathers. So the frequency of typhoon or rainstorm, so that is one or two, you know, the consequences of the climate change. And the water vapor, the energy comes from the sun. From the radiation to the liquid water becomes water vapor and then going around with the atmosphere area. Okay? For energy harvesting, there are quite a number of ways. And solar, wind, and you heard today also talking about piezoelectric. So that, this morning, Stephen talking about droplets. In fact, rain droplets can also generate electricity. And many other ways we could harvest energy depends on the quantity. What I talk about today, I only mentioned about a large quantity that affect regional or national, globally. But in your house, you could not use that much. A small amount of harvesting device could make the environment better. Why not? Or if 1 billion people, everybody helps the environment becomes good. Okay.
I don't think I can answer most of the questions, but I just want to pick up on the energy harvest. Yeah. Actually, I worked on this topic a little bit before I joined the current company. Actually, there's another field. Actually, is quite. I was working on thermoelectrics. You know, so that's actually another field that is quite useful to apply AI as well to screen huge amount of potential crystal structures that is good for thermoelectric, and they are actually quite a few that made it into pre-commercialization levels. So they can use different. Of course, the thermoelectric itself is a huge field. Depends how the application, what kind of thermal capabilities you're looking for. So it is something is being heavily researched, and a lot of talented groups are working on that. So, yeah. A lot of companies like Honeywell and GE have been working on this. I'm sure they will be. I think that the problem still is trying to, remember Professor Chen showed the chart when the price, goes down to, once it goes to certain level, you will see it everywhere, just like electric cars.
Yeah. Okay, thank you. And due to the time limitation, we have to conclude the panel discussion now. So let's thank Professor Chen and Dr. Gong again.
Okay, thank you very much for the thought-provoking discussion. May I invite all of you to remain on stage and pose for a group photo, please? May I invite our guests and our moderator, Professor Shao, to look at the official camera at the front. And just now, the speakers did mention that we have to dream big and we have to work step by step towards our goal. And now, may I invite all of them to look at the camera. Please keep looking at the camera with a thumbs up. Once again, thank you very much. That brings us to the end of today's event. I would like to invite Professor Shao to deliver the concluding remarks. Professor Shao, please.
Well, good afternoon again, everyone. So since YSH asked me to give the conclusion remarks, and it's the actually 6th of this sub-conference of the Young Academic of Science Summit. And this the whole day, actually, we have over 10 talks. This is great, and thank you for your participations, including our distinguished speakers and our audience. Right? Sorry that I missed the morning session because I went to Science Park. I missed the location. Okay, so today is the same as the advanced manufacturing and the new energy technology industry. Actually, a lot of talk that has showcased the cutting-edge innovations and also the transformative potential in these critical sectors. Right? So we learned a lot, and especially this afternoon's talk from the Jean-Marie Tascon and also Professor Chen Guihua and Gong Jindong. We actually, those are very seniors actually, not, as I said, not young, but it's a senior personnel that we learn a lot from them. Okay, so I would like to thank our co-organizers, the Great Bay Area Homeland Investment Limited, the Great Bay Area Homeland Youth Community Foundation, and the World Association of Young Scientists for their support and the collaborations. And also a thank to the Innovation and Technology Commission for the financial support and also the collaboration. And we also have a long list of supporting organizations, including all the universities in Hong Kong and S3 and the Cyberport, and also the Science Park and the Young Industry Council. So I'll not go the whole list. Okay. So this is actually the part of the second Young Academic of Science Summit. Right. So we organize the third Young Academic of Science Summit. Will start in this year, December. Okay. And so that we'll have, the 3 sub-conferences starting in March, June, and September next year. So we welcome you to also attending this conference. We have not, have the concrete rundown yet, but we announce and invite you again. So again, thank you very much for the participation, and have a good day. And thank you.
Thank you very much, Professor Chao. Please be seated. As we close, remember that the conversations started here today are just the beginning. The Young Academy of Sciences Summit aims to build a lasting community, and we encourage you all to stay connected through the Young Academy of Sciences to continue driving progress and collaborations. That concludes today's program. As Professor Chao mentioned, we look forward to seeing you at the 3rd Young Academy of Sciences Summit in December this year. Once again, thank you very much for your participation. Thank you.